Right, okay. So, can you hear me? Can you hear me? Right. So, today we are going to start exam target paper MCQ number one. So, let's see. Let's start from the question number one. So, these questions are really easy. Let's discuss one by one. Right. First question. Consider the following statements, number one and number two. The energy absorbed or released by atoms is quantized. Small particles under appropriate conditions show wave properties. Remember, the first statement they have given that energy is quantized, right? Energy is quantized. So this is the first statement. And the second statement they have given, so wave nature and particle nature of small particles. So you can see that energy is quantized, said by whom actually? That is by Max Planck. Max Planck is the person who said that energy is quantized, right? And the second statement, wave nature and particle nature of small particles. So that is actually mentioned by Louis de Broglie, right? We know about that. In the first unit, we have learned that Louis de Broglie is the person who said that what? Particle electrons are particulate as well as what? Wave nature. So therefore, so the answer that we can choose for the first question is second one, Max Planck and Louis de Broglie, right? So Max Planck and Louis de Broglie. So question number one, answer is first one. First one or second one? Second one, right? Question number two. The maximum number of electron pairs of an atom that are associated with principal quantum number n equal 3. Remember, we have learned under the quantum numbers, there are four main types of quantum numbers. There are four types of quantum numbers, right? So first one is principal quantum number, right? The second one is angular momentum quantum number, which is denoted as simple L. And the next one is magnetic quantum number, and last one is spin quantum number. So principal quantum number is representing principal energy level. Principal energy level. And azimuthal or angular momentum quantum number is representing sub energy level. Right? And the next one is magnetic quantum number. Magnetic quantum number is representing orbital time. Orbital time. Whether it is s orbital or p orbital or d orbital, we can represent that one using the magnetic quantum number. And the next one is spin quantum number. Spin quantum number is representing the rotation of the electrons. That means in an orbital, there are two electrons, isn't it? So these two electrons are rotating into two different directions. If I consider this electron is rotating into clockwise, other one is counterclockwise. So therefore, we can say that rotation, right, or direction of the electron. So these are the four main types of quantum numbers. In this question, they have given the maximum number of electron pairs of an atom that are associated with principal quantum number n equal 3. Maximum number of electrons associated with the principal quantum number n equal 3. So remember, students, here they have tried to say that this is the third principal energy level. They are asking indirectly how many electron pairs are there in the third principal energy level. In the first unit, we have learned that maximum number of electrons in a particular principal energy level is obtained by the equation 2n squared, right? So when you substitute here n equal 1, then total number of electrons are 2 into 1 squared, that is 2. If you consider the second principal energy level, 2 into 2 squared, so therefore 8 electrons are there. If you consider the third principal energy level, 2 into 3 squared, so therefore 18 electrons are there, right? So this is the equation that we can obtain now total number of electrons in particular principal energy level. So these are the electrons. So in the first principal energy level, there are 2 electrons. In the second principal energy level, there are maximum 8 electrons. In the third principal energy level, there are maximum 18 electrons. So in this question, they are asking the maximum number of electron pairs of an atom that are associated with principal quantum number n equal 3. They are asking about electron pairs. So there are 18 electrons. Then how many pairs are there? 9 pairs are there. So therefore, answer should be 5. Question number 2, answer is 5th one. Right? So these questions are very easy. Always in chemistry paper, remember the first 10 questions are very easy. First 10 MCQs are always easy, right? In any MCQ paper, first 10, first 15 MCQs are very easy. Okay. Really, there can be a difficult question, but most of the questions are very easy. Let's move for the third question. In the third question, they're asking the number of stable resonance structures that can be drawn for the oxalate ion, right? So they're asking the total number of stable resonance structures can be drawn for the oxalate ion. Oxalate ion is C2O4 2-, right? So let's draw, first of all, the Lewis structure for oxalate anion. Let's say what is the Lewis structure for oxalate anion, right? So we are discussing third question. In third question, they're asking how many stable resonance structures available for oxalate anion C2O4 2-. If I draw the Lewis structure for the oxalate anion, it's look like this. Carbon, there are 2 carbon atoms connected to 4 different oxygen atoms, and 2 oxygen atoms are having 2 negative charges in this way, right? And so these 2 oxygens are connected to the carbon atoms through a double. So this is the most stable Lewis structure that we can draw for oxalate anion. So they're asking total number of stable resonance structures we can draw for the oxalate anion. Okay, then I'm going to try another one. So I can shift the double bond here and single bond. I'm going to exchange this double bond and single bond in the left hand side, CO groups. So here I can make double bond, and here we have single bond. And this is negatively charged. Here we have 2 lone pairs. And what about this? Now we can have double bond here, and this is single bond, right? Okay. Let me try another one in this way. What about if I change the double bond and single bond here? In the first structure, I'm going to exchange the double bond and single bond. Then you will have the structure like this. Double bond, and this is the single bond, negatively charged, and this one remain as a double bond, and this is single bond. Okay, now we have obtained 3 structures. Can we draw another one? Yes, we can draw. Remember, these are stable structures, right? We can draw unstable structures also, but in this question, they're expecting us to draw only the stable structures. So therefore, what I'm going to do here, I'm going to draw in this way. What about if I make the 2 double bonds in horizontal? If I make the double bond between these 2 carbon and oxygens? Yes. So this is also possible, isn't it? And yeah, so these 2 oxygen atoms are having a negative charge. Right. So we have drawn 4 structures. Can we draw another one? What do you think about that? Can we draw another one? Actually, we cannot draw more further stable resonance structures for oxalate anion. There are 4 stable resonance structures for oxalate anion. In this question, they're expecting us to calculate the number of stable resonance structures that can be drawn for oxalate ion. So you can see that clearly we can draw 4 stable resonance structures Why we consider these four structures are stable? Tell me one reason to stability. So the reason is oxygen is having a negative charge. So among carbon and oxygen, who is the most electronegative atom? The most electronegative atom is oxygen. So that oxygen atom has a negative charge, which means this structure is very stable. Then these are the four stable resonance structures we can do for oxygen and iron. So question number 3, answer is third one. Easy. Question number 3, answer is third one. Very easy. Question number 4. Identify the pair of elements which has the largest difference in electronegativities. So they are expecting here to calculate, to find among which two elements has the largest difference in the electronegativities. Right. Okay. So electronegativity concept you learn in the first unit atomic structure. What does mean by the electronegativity? Electronegativity means simply when two elements are forming a chemical bond, the ability to pull the bonding electron pairs by a particular atom is considered as electronegativity of that particular atom. So what is electronegativity? Simply the ability to pull the bonding electron pairs. So you have to have an idea about the roughly you have to have an idea about the electronegativity values of few elements, right? If I consider hydrogen, here we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. We do not consider noble gases, right? Because noble gases are not forming chemical bonds, exception on. And then here we can consider sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Yeah, so these are enough. Yes, if you can remember these values, I think you can go for the answer. So you know that who is the highest electronegative atom, right? Who has the highest electronegativity value in the periodic table? Fluorine. You have learned that Pauling scale. Can you remember you learned that one in the first unit? According to the Pauling scale, fluorine is the highest electronegative atom in the periodic table. So the Linus Pauling has introduced a scale. According to that scale, fluorine's electronegativity value is 4.0. 4.0. So that value is considered as 4.0. Right? Now I will teach you a short method to remember these values, right? For these elements only. Yeah? Now you can consider that in a period actually, lithium, beryllium, boron, carbon, nitrogen, fluorine, second period. So the electronegativity values are decreasing by 0.5. Decreasing by 0.5. That means oxygen's value is 3.5. Nitrogen value is 3.0. Carbon's value is 2.5. Boron's value is 2.0. Beryllium is 1.5. Then lithium is 1.0. So likewise, we can easily remember the electronegative values of the second period if you know the electronegativity value of fluorine. Because fluorine is the highest electronegative atom which has the electronegativity value 4.0. Then oxygen having 3.5, nitrogen is 3.0, 2.5. Likewise, 0.5 by 0.5, the values are decreasing. And remember, particularly you have to remember that hydrogen's electronegativity value is what? Hydrogen's electronegativity value is 2.1. Students, you have to remember that one, right? Hydrogen is 2.1. And there is an element which has the same value as hydrogen. It is actually phosphorus. Phosphorus, hydrogen and phosphorus, both of them have the same electronegativity values. But remember, this is up to the first decimal point. If you consider the second decimal points, third decimal points, these values can be varied, right? But we consider, if I consider up to the first decimal point, hydrogen and phosphorus, both of them have same electronegativity value, right? Then look at this one. What about the electronegativity of sulfur and chlorine? That is also easy. You're going to subtract one value from this fluorine's electronegativity value, then you will obtain chlorine's electronegativity, which is 3.0. And sulfur, same as before, 2.5. You are going to subtract one value. Then you can obtain sulfur's electronegativity value is 2.5, Chlorine is 3.0. And then hereafter, you can subtract 0.3 by 0.3, right? Electronegativity values are decreasing by 0.3, right? Then tell me the values. What are the values? Silicon is 1.8, aluminium 1.5, magnesium 1.2, sodium is 0.9. So if you can remember these values, you can go for the answer, right? So it's not difficult to remember these values, right? So we know that there is a pattern. If you can remember the pattern, you can easily go for the answer. So this is not difficult, right? What you have to remember, fluorine is the highest one, 4.0. In the second period, electronegativity values are decreasing by 0.5. Hydrogen, phosphorus, both of them have 2.1. And under oxygen, we have sulfur, which is less than electronegativity 1 value. From the oxygen, 2.5. So chlorine is 3.0. Other than that, after phosphorus, the previous elements in the third period, their electronegativity values are obtained by decreasing 0.3 from the phosphorus value. So therefore, very easy. So this is a pattern. Remember this pattern. Now, let's go for the question. Identify the pair of elements which has the largest difference in electronegativity. Let's go one by one. Boron and aluminium. So what is the difference? Boron and aluminium? 0.5. Next one is beryllium and aluminium. Beryllium and aluminium electronegativity value difference is 0. Because you can see that both of them have the same electronegativity values, right? Can you tell me the reason? Any reason? Their chemical properties are same, right? Can you remember the diagonal relationship you learn in inorganic chemistry? Diagonal relationship. Beryllium and aluminium, even though these two elements are in two different groups, they have same chemical properties because they are diagonal elements like lithium and magnesium, and beryllium and aluminium, both of them are amphoteric elements. Boron and silicon. So what is the electronegativity difference between boron and silicon? So that is 0.2. And the next one is aluminium and carbon. Let's see, aluminium is 1.5, carbon is 2.5. So actually the difference is 1.0. Yes, the highest difference belongs to aluminium and carbon. Okay, I didn't consider boron and carbon. Let's consider that one also. Boron and carbon, the difference is 0.5. So we can see that aluminium and carbon has the highest electronegativity difference between these elements. So the answer is number 5. Question number 4, answer number 5. Okay, now I'm moving for the question number 5. Question number 5, if you have done past papers properly, I think you have already met this question. Always I'm recommending to do the past papers because if you analyze the examination paper, this year paper, 2023 paper, January they kept the examination. All of the MCQs are past papers. If you have analyzed the past papers properly, so no one can say that paper is difficult, right? Paper is in a standard state, actually standard way. So paper is really easy if you have done past papers properly. So therefore, this question number 5 is exactly 2019 A-level past paper question. Let's see what we have to learn under this question, right? So that's a calculation part. Let's see. Titanium tetrachloride reacts with liquid magnesium metal. Give titanium metal and magnesium chloride liquid at high temperature. Okay, let me write down the reaction that they have given. Question number 5. Titanium tetrachloride, TiCl4 gas. This is reacting with liquid magnesium to produce titanium metal and magnesium chloride liquid magnesium chloride. So this is the reaction that they have given. So how many chlorine atoms are there? In the left hand side, there are 4 chlorine atoms. Therefore, let me put here 2. And how many magnesiums are there now? 2 magnesium and 1 titanium. So the reaction is balancing, right? So when you are doing chemical calculation questions, when you write a reaction, always try to remember that you have to write down the balance chemical reaction, right? When 0.95 kilograms of titanium tetrachloride gas is made to react with 97.2 magnesium liquid. So they have used here 0.95 kilogram means 950 grams. Magnesium liquid mass is 97.2. So these are the masses. The reactant that is completely consumed, this is commonly referred to as limiting reactant or limiting reagent. Can you remember? In chemical calculations, you learn limiting reagent or limiting reactant. So this question is based on the limiting reagent, right? If you have done enough calculations in the 3rd unit, so these questions are nothing, right? They're asking about the limiting reagent and the amount of titanium metal formed respectively are. They have given the molar masses of titanium tetrachloride. Molar mass of titanium tetrachloride is 190 grams per mole, and molar mass of magnesium is 24.3 grams per mole. And here molar mass for titanium, that is 48 grams per mole. So these are the additional data values they have given. So why they have given molar mass values? What is the reason? So the reason is we have to find out the number of moles, right? By looking at the masses, we cannot decide the limiting reagent, right? By looking at the mass, we cannot decide the limiting reagent. We have to decide the limiting reagent by considering how much of moles added from this each reactor, right? So let me consider initial moles. Initially, how much of moles they have added? So 950 grams divided by, so the molar mass is 190 grams per mole. So magnesium mass is 97.2. Molar mass they have given 24.3 grams per mole. Grams will cancel off. Then you can see that. So here 19 into 5 is 95. Yeah, if you divide 95 by 19, answer is 5. Yes, 5 moles, isn't it? Right. And what about this 24.3? So this is actually 4, right? Because 24.3 multiplied by 4 means 12, 1, 16, 17, 1. Yes. So there are 4 moles of magnesium. So these are the initially added moles of titanium tetrachloride and magnesium. So as I mentioned you, what does mean by the limiting reagent? Remember students, always limiting reagent is the one who deciding the reaction. How it decide the reaction? Normally, limiting reagent is totally consuming in the reaction, right? We are adding extra amount of some reactants in a reaction, right? So the limiting reagent is the one who deciding how much of extent that reaction should occur. So we can identify that one because limiting reagent or limiting reactant is finally consumed. Finally, we cannot find that limiting reagent. Totally consumed. See, they have given, this is commonly referred to as limiting reactant, which is completely consumed. So, according to the reaction stoichiometry, what is the reaction stoichiometry between titanium tetrachloride and magnesium? Reaction stoichiometry is 1:2. 1:2 is the reaction stoichiometry. Then we can find out here the reacted and the formed amount. Reacted and the formed number of moles. Okay, you can see that according to the stoichiometry ratio, there should be 1 mole of titanium tetrachloride reacting with 2 magnesium. Then just imagine, let's consider magnesium. There are 4 moles of magnesium. There are 4 moles of magnesium, right? So here, how many titanium tetrachloride we need? 2 moles, isn't it? Right? So therefore, we can see that magnesium is consuming. If I consider in the opposite way, 5 moles of titanium tetrachloride are there. So there should be 10 moles of magnesium in order to react with total 5 moles of titanium tetrachloride. So therefore, you have to understand the one who totally consuming in this reaction is magnesium. Got it? So the one who completely consuming in this reaction is magnesium, not titanium tetrachloride. Again, listen to this. If I consider 5 moles of titanium tetrachloride, according to the reaction stoichiometry, there should be 10 moles of magnesium, but we don't have 10 moles. Then let's go with magnesium. There are 4 moles of magnesium. We need half amount of titanium tetrachloride, that is 2 moles, but we have extra amount, therefore no need to worry. So the total consumed one is magnesium. Total consumed one is magnesium, right? So the reacted amount is 4 moles. According to the reaction stoichiometry, you can see that titanium tetrachloride reacted amount is. So titanium metal formed amount, that is also 2 moles. Magnesium chloride, 4 moles. Right? So the negative signs are representing reacted, positive signs are representing, that is 4. And finally, we can get here the remaining ones. Remain number of moles. So magnesium totally consumed, titanium tetrachloride remaining 3 moles, and titanium metal is remaining 2 moles. So the one who completely consuming in a reaction is considered as limiting reagent. So therefore, magnesium liquid is the limiting reagent. They have asked here, what is the limiting reactant? And the amount of titanium metal has been formed, right? What is the number of moles of titanium? 2 moles. We know the molar mass. We know the equation number of moles is equal to mass divided by the molar mass. And then mass equal number of moles multiplied by the molar mass. 2 moles multiplied by 48 grams per mole. So per moles will cancel off. Answer is 96 grams. So the mass of titanium formed here, it is 96 grams. So therefore, question number 5, answer is second one. Question number 5, answer is second. How 3 mole came? Because from 5 moles, so you can see that from 5 moles, 2 moles are reacted. After reacting 2 moles of from 5 moles, the remaining ones are 3. Got it? So here I have written here remaining number of moles. Got it? Right. So this is question number 5. right? Okay. So question number 6. Let's see. Question number 6. The ideal gas equation can be expressed in the form of P equal rho RT over capital M, where rho is the density of the gas, capital M is the molar mass of the gas, P is the pressure, and T is the temperature. If the units of R are joules per mole per Kelvin, units of rho in this equation should be right. Okay. So in gas laws, unit for gaseous state of matter. So this is a simple equation that we can derive from the ideal gas equation. We know that ideal gas is equation is PV equal nRT. We are familiar with this equation, PV equal nRT. So this is ideal gas equation. PV equal nRT, ideal gas equation, right? So in this ideal gas equation, we can derive the density of gas. How we can do that one? We know that number of moles can be written as mass divided by molar mass, isn't it? So then PV equal M over capital M RT, M over M capital RT. Then P equal, right? We can take here M RT V capital M. We know that M over V. What does it mean by M over V? M over V means mass divided by the volume. So mass divided by the volume is density, rho. So they have given the symbol here, rho, RT over capital M. So this is the equation that they have derived. Okay. So we don't have to derive that one. They have already given this. But this is the way that we should know this one, right? So in a past paper here, I think a very recent past paper 21 or 22, they have given in structured acid paper derive an equation, right, for density or something, right? So this is the way that we can derive. So they're asking what is the units of rho in this equation, right? So rho equal Pm over RT. So what is the unit of P? If I consider unit of rho, right, and units of these things. So what is the unit of pressure? Newton per square meter. What is molar mass? Molar mass, we can consider that one as grams per mole. They have given that already. And what is universal gas constant? R. They have given joules per mole per Kelvin. And temperature is measured by Kelvin. So per Kelvin, Kelvin will cancel off. Per mole will cancel off. We know that, students, Newton, right? So Newton per square meter, gram, here joule means Newton meter. In physics also you have learned that joule is equal to Newton meter, the units. Then Newton will cancel off. Then unit of rho is equal to grams per cubic meter. So the answer should be second one. See how easy these questions are. Question number 6, answer is second one. Unit of rho is grams per cubic meter. Right? Unit of rho is grams per cubic meter. Question number 7. The electron pair geometry and shape around the two nitrogen atoms labeled as N1 and N2 in the molecule H2NNO. Let's see, right? So we are done with this one, right? This is very easy. The electron pair geometry and shape around the two nitrogen atoms in molecule H2NNO. Right. Look at this. Question number 7. So molecule is H2NNO. So skeleton is given. Let's draw the Lewis structure. So the Lewis structure of this molecule is like this, NO, right? Two lone pairs on oxygen in this way, right? So what is the shape if I consider these two nitrogen atoms? First of all, shape. First of all, electron pair geometry. Let's consider electron pair geometry. And then shape, right? So electron pair geometry around first nitrogen atom. This is the first nitrogen atom and this is the second nitrogen atom. Electron pair geometry for this nitrogen atom. This is equal to 1, 2, 3, 4. How many Vesper pairs are there? 4 Vesper pairs are there. Therefore, electron pair geometry is tetrahedral. And what is the shape? So one lone pair is there. So therefore, shape is trigonal pyramidal. Next one. Here we have the second nitrogen atom. What is the electron pair geometry? There are 3 Vesper pairs. 1, 2, 3. We do not consider pi bonds when we consider the Vesper pairs and electron pair geometry. So therefore, there are 3 Vesper pairs. 1, 2, 3. Electron pair geometry is trigonal planar. Trigonal planar. And what is the shape? Shape is angular. Angular because there is a lone pair, right? So this is the shape and electron pair geometry for this nitrogen atom, and this is the shape and electron pair geometry for this nitrogen atom, right? So answer we can choose that they're asking about here electron pair geometry and shape around 2 nitrogen atoms, right? Tetrahedral, trigonal pyramidal, trigonal planar, angular. Answer is first one. Question number 7. Answer is first one. Very, very easy. Second unit, shapes of molecules. Let's move for the question number 8. Let's see. Question number 8. The correct answer when the chemical species sulfur dioxide, sulfur trioxide, sulfite, sulfate SO4 2 minus, and sulfur dichloride are arranged in the increasing order of the electronegativity of sulfur, right? Students, remember, when we consider the electronegativity, let's quickly revise the theory related to the electronegativity. There are 4 factors affecting to the electronegativity. Number 1 is hybridization. And the second factor is oxidation number. And the third factor is formal charge. And the fourth factor is surrounding atoms, nature of the surrounding atoms. Right? So these are the 4 factors which are affecting to the electronegativity. Let's see how they are affecting to the electronegativity. If you consider the hybridization, when S character increases, electronegativity increases, right? When S character increases, electronegativity increases, right? Oxidation number. When oxidation number increases, electronegativity increases. When formal charge increases, electronegativity increases. And what about the surrounding atoms, right? So I will explain that one using a simple example. Just imagine carbon tetrachloride and carbon tetrafluoride. If I ask you which carbon atom is more electronegative, right? Which carbon atom is more electronegative among these two molecules, CCl4 and CF4? So the answer should be, which one is more electronegative? Carbon atom in CF4 molecule. So the reason behind it is fluorine is more electronegative. Since fluorine is more electronegative, fluorine is pulling electrons from carbon. Since it is pulling electrons from carbon, carbon is becoming more electropositive. That means carbon is positively charged, not electropositive. Carbon is positively charged. So if it is positively charged, carbon can easily pull the electrons from the others. So therefore, we can understand that here clearly this carbon atom is the most electronegative carbon atom. So when the surrounding atoms are becoming electronegative, central atom is becoming electronegative too, right? So therefore, these are the four factors affecting to the electronegativity. And always the dominant factor, the major factor is hybridization. Now, in this given molecule, sulfur dioxide, sulfur trioxide, sulfite, sulfate, and sulfur dichloride, let's consider first of all hybridization. Using hybridization, we can categorize them. Let's see. If I draw the Lewis structure, sulfur dioxide is look like this. Okay. Sulfur trioxide and sulfite and sulfate. I'm not going to mention all the lone pairs here. And sulfur dichloride is look like this. Students, you can see that sulfur dioxide is sp2 hybridized. Sulfur trioxide is also sp2 hybridized. Sulfite sp3 hybridized. Sulfate sp3 hybridized. Sulfur dichloride sp3 hybridized. So therefore, you can take these three molecules separately and these two molecules separately. Why? Because when I'm considering these two molecules, right, sulfur dioxide and sulfur trioxide, their hybridization is sp2. S character is high. So therefore, we can consider that they have highest electronegativity sulfur atom than these three, right? Than sulfite, sulfate, and sulfur dichloride, sulfur dioxide and sulfur trioxide has the highest electronegativity. So these two have the highest electronegativity. Now, among these two, which one has the highest electronegativity? For that, let's consider the oxidation number, the second factor. Oxidation number for sulfur atom here is +4, and this one is +6. I told you that when oxidation number increases, electronegativity increases too. Therefore, sulfur trioxide has the highest electronegativity, sulfur, and then sulfur dioxide. And now you can compare these three, right? If I consider the oxidation number of sulfur here, that should be +4, and this one is +6, and here oxidation number is +2. Then you can decide which one has the highest electronegativity. Of course, that is sulfate. And next one is sulfite. And the last one should be sulfur dichloride. So this is the variation. Electronegativity of sulfur varies. Electronegativity of sulfur. Okay. So the answer should be fourth one. Question number 8, answer is fourth one. Right. Okay. Now let's move for the question number 9. Question number 9. Question number 9 is also a chemical calculation question. Let's see. A 25 grams of sample of polluted air containing ozone is treated with an acidic solution containing excess potassium iodide. Ozone is converted to oxygen and water during this reaction. The iodine liberated is titrated with 0.002 moles per cubic decimeter sodium thiosulfate solution. Volume of sodium thiosulfate required was 25 cubic centimeter. The mass percent of ozone in the air sample is. Let's see. Let's summarize what they have given in this question. First of all, 25 grams sample of polluted air containing ozone. So this ozone is treated with potassium iodide. Ozone treated with potassium iodide in the presence of acidic medium. Yeah, acidic solution, therefore H plus is there. And it's converted to oxygen and water. Oxygen and water. The liberated iodine, that means I minus, has been converted to iodine. That's what meant by liberated iodine. They have given that iodine has been liberated. So this liberated iodine reacted with sodium thiosulfate, S2O32 minus, thiosulfate anion. So this is very famous reaction. It is converted into I minus again and tetrathionate S4O62 minus. To balance reaction, we can put here 2 and here 2 as well. So then the reaction is balanced. What about the previous one? To balance this one, we can put here 2 H pluses and 2 I minus. The reaction is balanced. Okay. So they have given the concentration of sodium thiosulfate solution and the required volume. So according to the equation, we know that C equal N over V, concentration is equal to number of moles divided by the volume. Right? You know about this famous equation you learn in chemical calculations, right? And then we can calculate the number of moles of thiosulfate. When you multiply the concentration 0.002 moles per cubic decimeter multiplied by the volume is 25 into 10 to the power minus 3 cubic decimeters. Then answer should be, what should be the answer? So here we have 10 to the power 5. 15 to the power 5 means 5 into 10 to the power minus 4 moles reacted with iodine. Right? You can see the stoichiometric ratio. Thiosulfate and iodine stoichiometric ratio is 2:1. So then number of iodine moles are half of that. 5 over 2, 10 to the power minus 4 moles. So these are the number of iodine moles. 5 over 2, 10 to the power minus 4 moles. Right? These are the number of iodine moles. Now according to this first reaction, iodine and ozone stoichiometric ratio is 1:1, which means number of ozone moles will be 5 over 2, 10 to the power minus 4 moles. These are the number of ozone moles. Right? These are the number of ozone moles. So now we can calculate the mass of ozone because we need to find out the mass percentage of ozone. 5 over 2, 10 to the power minus 4 moles multiplied by, what is the molar mass of ozone? Oxygen is 16. 16 into 3 is 48 grams per mole. So per moles will cancel off. And here 2, 24. When you multiply 24 by 5, the answer is 120 into 10 to the power minus 4 grams. So therefore we can say that 1.2 10 to the power minus 2 grams. So this is the mass of ozone that you will obtain. But students, they are asking about mass percentage of ozone. What is the total mass of the sample? 25. Out of 25, mass of ozone is 1.2 10 to the power minus 2 multiplied by 100%. Right? Then you will obtain the answer here. We'll cancel off. So 1.2 divided by 25. What is the answer? 0, 0. So 0 for 200, how many? 8, right? So therefore, answer should be, sorry, this one should be 0. So 120. So 400 and for 208. Yes. Then answer should be 4.8, right? Into 10 to the power minus 3 percentage. So this is the percentage, right? Question number 9, answer is first one. Shall we move for the question number 10? Which of the following reaction steps is not present in the Bonn-Haber cycle of sodium chloride solid formation? Right. Do you know how to construct the Bonn-Haber cycle for sodium chloride? Right. What is the purpose of constructing Bonn-Haber cycle? What is the purpose of constructing Bonn-Haber cycle? What is it? So the purpose of constructing Bonn-Haber cycle is to find out lattice enthalpy, right? Lattice enthalpy of ionic solids. We know that ionic compounds are forming ionic lattice. So in order to find out the energy of these ionic lattices, we can use Bonn-Haber cycle. So let's see how we can construct the Bonn-Haber cycle for sodium chloride. Question number 10. Sodium solid chlorine gas is forming sodium chloride solid, right? So this is formation enthalpy. from the reference form of the elements, it's forming sodium chloride. So we can put here half, then the reaction is balanced. So this is delta H theta F, formation enthalpy of sodium chloride, right? Formation enthalpy of sodium chloride solid, delta H theta F. And here we have sodium gas, and let me consider chlorine gas. So sodium solid to sodium gas, this is sublimation enthalpy, delta H theta SUB, right? And then here we should have Cl minus gas and Na plus gas, right? From this one only, we consider this is lattice enthalpy, delta H theta L, sodium chloride, lattice enthalpy. So when we consider the lattice enthalpies are forming from the gaseous state cation and the gaseous state anion, right? Then what about this chlorine gas to chlorine, just atom, one atom? We can consider this is actually atomization enthalpy of chlorine, and this is sublimation enthalpy of sodium solid. So what about this? This is electron gain energy, delta H theta, electron gain enthalpy, first one, of chlorine, right? And what about this? This is ionization enthalpy, delta H theta I1 of sodium solid, right? So this is Born-Haber cycle. So now we can apply Hess law. We can say that from Hess law, all these summations are equal to formation enthalpy. Delta H theta F, sodium chloride solid, this is equal to delta H theta sublimation enthalpy of sodium solid plus atomization enthalpy of chlorine gas then electron gain energy of chlorine plus ionization enthalpy of sodium solid plus lattice enthalpy of sodium chloride, right? So sometimes in the examination, they will give you these values. They will give you formation enthalpy. They will give you atomization enthalpy of chlorine, ionization enthalpy of sodium, electron gain energy of chlorine, sublimation enthalpy, and they will ask what is the lattice enthalpy. Or else they can give any other values to find out any other term. After constructing the Born-Haber cycle, others are easy. By applying his law, if you know the values, you can get the answers. Very easy. So in this question, they're asking which of the following reaction steps is not present in the Born-Haber cycle? What about the first one? First one, they have given Na plus aqueous Cl minus aqueous is forming sodium chloride aqueous. Students, here do we have hydration enthalpies? Do we have aqueous means what? Water, hydration enthalpy, solvation enthalpy, nothing is there. So therefore, this is not related to the Born-Haber cycle of sodium chloride. So that should be the answer. Others are okay. Second one, sodium solid to sodium gas, sublimation enthalpy. Third one, chlorine gas to Cl gas, that is bond dissociation enthalpy. Yes, we can consider this one as atomization enthalpy or half of the bond dissociation enthalpy. Fourth one, electron gain enthalpy of chlorine. Fifth one is lattice enthalpy of sodium chloride. So therefore, answer should be first one for question number 10. Is number 1. Answer is number 1. Right. Next question. Question number 11. Which of the following elements has the lowest third ionization energy? Magnesium, neon, nitrogen, phosphorus, fluorine. Right? How do you choose the answer? Which of the element has the lowest third ionization energy? Remember, since we are discussing about here ionization energy, I'll go for the ionization energy graph. Can you remember the ionization energy graph? First ionization energy graph. This is the way that ionization energy varies. A zigzag variation you can see between these elements. Helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So you can see the same variation for the third period elements also. Right? So if I draw that one, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, fluorine, argon. So likewise, you can see the same repeating variation for the third period elements also, right? So you have to remember as a summary, always ionization energies group wise, in which group has the highest ionization energy and which group has the lowest ionization energy. Let's consider I1, I2, and I3 ionization energies. Okay, so always remember the highest ionization energy, first ionization energy, belongs to group 18 elements. Highest in which group? Highest in group this one. Highest in group this one. So the highest in group 18, first ionization energy, and the lowest in group number 1. If you go for the second ionization energy, lithium will go here. So therefore the highest in group number 1, beryllium come down. So therefore second group is the lowest one. If you go for the third ionization energy, highest in group 2, lowest in group 13. This is the way. You have to remember this one as a summary. Now, so these are atomic number, and this is I1, first ionization energy, kilojoules, right? Which of the following has the lowest third ionization energy? Lowest third. Sorry. Now, if I draw the third ionization energy graph, how we can draw the third ionization energy graph? Then we can shift lithium here, then second ionization energy, beryllium here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, and aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. So this is the third ionization energy graph, right? In first ionization energy graph, the peak belongs to helium. In second ionization energy graph, the peak belongs to lithium. Now beryllium will go there in the third ionization energy. Now they are asking, what are the elements they have given? Magnesium, neon, nitrogen, phosphorus, and chlorine. So you can see that phosphorus has the least ionization energy according to the graph, right? Phosphorus has the least third ionization energy. Let's consider the electron configuration of phosphorus. Phosphorus 15, 1s2. 2s2, 2p6, 3s2, 3p3. Yeah, after removing 2 electrons from this one, you are going to remove the 3p1 electron. So therefore, no issue, not stable configuration. So therefore, we can easily remove the electron. So therefore, ionization, third ionization energy is, yeah, that is a little bit lower. But if you consider the first ionization energy, since it has half stable configuration, it has some kind of a high value. So therefore, question number 11 asks is fourth one. Question number 12. Which molecule from the molecules given below consists the highest number of pi bonds? Which molecule from the molecules given below consists the highest number of pi bonds? That's very easy. They're asking in which molecules there are a highest number of pi bonds. Let's see. Question number 12. So first of all, they have given sulfuric. Right? And then they have given sulfurous. And next one is HNO3. Right? Next one, phosphoric acid, H3PO4. Phosphoric H3PO4. And the next one is perchloric acid, HClO4. Perchloric acid. Right? Now you can see that. So this is HClO4. Now you can count the number of pi bonds. So which one has the highest number of pi bonds? In sulfuric, there are 2 pi bonds. Okay. In sulfurous, how many pi bonds? Just 1. In HNO3, just 1 pi bond. In phosphoric acid, how many pi bonds? Just 1. In perchloric acid, how many pi bonds? There are 3 pi bonds. So therefore, answer is number 5. Question number 12, answer is number 5. That's very easy. You have to count the number of pi bonds. See how easy these 3 questions are. Question number 13, which statement is true regarding tetrahydroxydoaluminate? Question number 13. They're asking which statements are correct related to this tetrahydroxydoaluminate. Got it? So, if I draw the structure for this one, aluminium 3 plus cation, This is surrounded by 4 OH minus groups. Okay. So we can consider that electrons are given, and now it's forming a bond like this, right? Now aluminium's charge is negative. Okay. So the central atom is sp2 hybridized. Is that correct? No, wrong, because this is sp3 hybridized. Its total number of total lone pairs electron is 8. 1, 2, 3, 4, 5, 6, 7, 8. If you consider the oxygen atoms, yeah, there are 8 lone pairs. The second statement is correct. But let's go for the others also. It contains d electrons. Yeah. Is that correct? No d electrons. Why? Aluminium belongs to p block. Oxygen belongs to p block. Hydrogen is in s block. So how it can be d electrons? So therefore, that statement is also wrong. The number of sigma bonds are 4. You can see that actually there are 8 sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8. Wrong. The total number of electrons in the valence shell is 28. Is that correct? In the valence shell of aluminium, there are 8 electrons. And here we can consider 8. Here we have 2. Here we have in each we have 6. So therefore 6 into 4 is 24. 24 plus 8 is 32. But they have given 28. That is wrong. So question number 13 answer is second. These are very, very easy questions. Not difficult. Right. Now let's move for the question number 14. Question number 14. The mole fraction of ammonium nitrate is 5/6 in a solid mixture that consists only ammonium nitrate and calcium carbonate. So there is a mixture which is containing ammonium nitrate and calcium carbonate, right? So they have given that mole fraction of ammonium nitrate is given as 5/6. So therefore we can understand mole fraction of calcium carbonate is 1/6. So the mass percentage of calcium carbonate, how we can find it? We have to find out mass percentage. How we can find it? So let's take in this way, right? So let's assume number of ammonium nitrate moles are 5 and number of calcium carbonate moles are just 1 mole, right? Then you can find out mass of ammonium nitrate. First of all, let's take what is the molar mass of ammonium nitrate. Molar mass of ammonium nitrate is, there are two nitrogens, 14, 14, 28, 28, and oxygen is 16 into 3 is 48, 4. So therefore 12, 20, so 80 grams per mole. That is the molar mass of ammonium nitrate. And the next one, calcium carbonate. Calcium carbonate is calcium 40, carbon 12, 48, 100 grams per mole. Right? Then if you multiply this one by the molar mass 100 grams per mole, per moles will cancel off. Then calcium carbonate mass of, sorry, right? Is a number of moles. So let's calculate mass of ammonium nitrate. 5 moles multiplied by mass is 80 grams per mole. So per moles will cancel off. Therefore 400 grams. So this is mass of ammonium nitrate. And you can find out the mass of calcium carbonate because molar mass is 1 mole. Molar mass is 100 grams per mole. So then you can see that mass of calcium carbonate is 100 grams. So they're asking what is the mass percentage of calcium carbonate? Calcium carbonate mass percentage. What is the total mass? Total mass is 500 grams. Out of 500 grams, calcium carbonate mass is 100 grams. So cancel off multiplied by 100%. So the answer should be 20%. So 20% of calcium carbonate is there in the sample. Right? So 20% of calcium carbonate is there in the sample. Question number 14 answers first. Right, okay. Now let's move for the question number 15. So in the question number 15, they have given that consider the following bond energies at 25 degrees Celsius. So this question is related to enthalpy. Bond, they have given three types of bonds. Question number 15. The bond dissociation enthalpies are given. Bond energy means here bond dissociation enthalpies. They have given 150, 250, and here 200 kilojoules per mole. So these are the bond energies, right? So they're asking what is the enthalpy change? What is the enthalpy change of this reaction? A2, 3B2, and it's forming 2AB3. Yes, right, okay. Since they have given the bond dissociation enthalpies, we have to do this question using the bond dissociation enthalpies. Right? Right. So A bond, and here we have B bond, three types of bond, and AB3 bond, two of them. Right. So we can find out the enthalpy change of this reaction. We can find out enthalpy change of this reaction delta H theta is equal to bond dissociation enthalpies, right, of bonds broken. Right, we know that in the reactant side these bonds are breaking, right, and newly these bonds are formed, plus sigma delta H theta D bond dissociation enthalpy of bonds formed in the right hand side, new bonds are formed. Then we can substitute the values. So what are the dissociation enthalpies of the bonds broken? AA bond is broken, energy is 150. BB bond is also broken, so therefore 3 into 250 plus AB bond is also broken, but there are 6 bonds, so therefore 200 into 6. And now we can find out the enthalpy change of this reaction. Right? What it should be. So this one should be negative, isn't it? Negative. This one should be negative, right? So what is the answer? 150 plus 250 into 3. So therefore 750 plus 150, 900. And here we have 1200 kilojoules per mole. So therefore answer is minus 300 kilojoules per mole. So this is the enthalpy change of the reaction. Minus 300 kilojoules per mole. Question number 15 answer is first one. right? Question number 15 answers first one. Right. Now let's move for the question number 16. Question number 16. Which of the following is correct for the energy range of a photon of visible light in the wavelength range lambda 1 to lambda 2, where lambda 2 is greater than lambda 1? So they're asking energy range, that means energy gap, right? Okay, let's see. So this is related to that energy equation we learned in first unit. Can you remember that equation? Right? E equal hc over lambda, right? So this is the equation. So E means energy of a photon, just one photon, na? And H means Planck's constant. Value is 6.626 10 to the power minus 34 joule seconds, right? And C means velocity of light, 3 into 10 to the power 8 meters per second. And the next one is lambda wavelength, right? So this is the energy equation, equal hc over lambda. So they have given that there are two waves, lambda 1 and lambda 2, which is corresponding to visible light region. So they're asking energy range. Energy range means the energy gap, delta E, right? And they have given that lambda 1 is less than lambda 2. We know that according to that equation, what is the relationship between lambda and energy, wavelength and energy? Planck's constant, velocity of light, both of them are constant values. So therefore, lambda wavelength is inversely proportional to the energy. So therefore, when the wavelength decreases, energy increases. So they have given that lambda 2 is greater than lambda 1, then E1 is greater than E2. So delta E is equal E1 minus E2. Now we can write down the equation corresponding to energy of first wave, hc over lambda 1 minus hc over lambda. But remember, students, they have given this lambda using nanometers. They have given this one in nanometers. So normally energy is measured by joules, right? So in order to get this correct exact unit, we have to multiply this one by 10 to the minus 9, because I want to convert this one into meters. That's why I'm going to multiply this one by 10 to the power minus 9. Try to understand, okay? I have converted lambda, which is given by nanometers, into meters. Then only I can get the correct unit, joules, right? Now, we can see that HC is a common factor. Then here we have 1 over lambda 1 minus 1 over lambda 2. And in the denominator, 10 to the power minus 9 is a common factor. If I take that one onto the numerator, then 10 to the power plus 9, right? So joules, you can see that this answer is given in the first answer in the question. Question number 16, answer is first one. Question number 16 asks this first one. Question number 17. Which of the following electron transitions belongs to the visible region of the line spectrum of atomic hydrogen? So this question is related to hydrogen's emission spectrum. Let's see. Let's see hydrogen emission spectrum. Question number 17. So we can draw the emission spectrum, the energy level diagram in this way. Right. So all the electron transitions falling to the first principal energy level belongs to the Lyman series, right? All the electron transitions which are falling to the first principal energy level, that is belong to the Lyman series, right? So this is first principal energy level, n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, and n equal 6, right? And then all the electron transitions which are possible for the second principal energy level, they are belongs to the Balmer series, right? So this is Lyman and this is Balmer. And all the electron transitions which are falling to the third principal energy level, that is Paschen, right? All the electron transitions which are possible to the fourth principal energy level, bracket, and electron transitions which are possible for the fifth principal energy level. So these are the actually main 5 series we learn in hydrogen emission spectrum, right? Lyman, Balmer, Paschen, bracket, Fun. So Lyman series belong to the ultraviolet region in electromagnetic spectrum. Balmer series, the 4 spectral lines, the very first 4 spectral lines belong to the visible light region, right? Visible light region. So this is known as H alpha, right? This is H alpha, which is red color. And then the next line is green color, H beta. And the next one is blue color, H gamma. And the last one is H delta, which is violet color. So we can see these 4 lines for our naked eye because they are belongs to the visible light region. H alpha, H beta, H gamma, H delta, red, green, blue, and violet. So Paschen series belong to the infrared region. Bracket also infrared, fund also infrared. Right? Now the question is, which of the following electron transitions belong to the visible region of the line spectrum of atomic hydrogen? So first one is n equal 5 to 3. 5 to 3 is actually, we can consider it as partial. N equal 1 to 2. N equal 1 to 2 is absorption spectrum, not emission spectrum, that is Lyman. And n equal 2 to 1, is that correct? 2 to 1 is belong to Lyman series. 4 to 2, yes, 4 to 2 means this one. 4 to 2 means the green color one, H beta, that is belong to the visible light region. N equal 3 to 1, that is also Lyman. So therefore question number 17 answer is, according to the answers, they that one is second one. Yes. Right. Question number 17 is like this. So question number 18, next one. Question number 18 belongs, statement type of questions. So they're asking, select the correct, incorrect statement, right? Look at this. Pauli exclusion principle excludes the possibility of the presence of a third electron in an orbital. That is correct. Pauli exclusion principle excludes. It's not saying that anything related to the presence of a third electron, right? So therefore, Pauli exclusion principle exclude the possibility of the presence of third electron. Yeah, that is correct. Second statement, in a potassium atom, the number of electrons having quantum numbers n equal 3 and ml equal 0 is 4. If you consider potassium atom, potassium's electron configuration, potassium atomic number 19, configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So this is the electron configuration. And they have given that number of electrons having quantum numbers n equal 3 and ml equal 0. Third principal energy level, and ml equal 0 means this is s orbital. In third principal energy level, you can see that s and p orbitals are filled with electrons. So this is actually related to a s orbital. So this is a ml equals 0. Ml equals 0 means what? In s sub energy level there is an s orbital which is named as 0. In p sub energy level, -1, 0, +1. So therefore, the maximum number of electrons are 4. But yeah, they have given it correctly, right? So they have given the in a potassium atom the number of electrons having quantum numbers n equal 3 and ml equal 0, that is 4. There are 4 electrons. So that statement is correct. Third one, the effective nuclear charge felt by a valence electron in nitrogen is greater than the effective nuclear charge felt by a valence electron in carbon. What do you think about that? The effective nuclear charge felt by nitrogen is greater than effective nuclear charge felt by valence electron in carbon, right? So effective nuclear charge. Effective nuclear charge is equal to EFF, ZEFF is equal to nuclear charge minus shielding effect. Nuclear charge is denoted by Z. Shielding effect is S. So therefore, ZFF is equal to Z minus S. Right? So remember, students, the connection between effective nuclear charge and the atomic radius. Radius is inversely proportional to the effective nuclear charge. When radius increases, effective nuclear charge decreases. Try to understand. Okay. So then let's compare carbon and nitrogen. What is the effective nuclear charge for carbon? Right. Carbon electron configuration is carbon 1s2, 2s2, 2p2. Nuclear charge is 6 because number of protons are 6. So how do you calculate the shielding effect? Shielding effect means number of co-electrons. Number of co-electrons means except valence shell electrons, others are considered as co-electrons. Co-shell and valence shell. Valence shell is the second principal energy level. So co-shell is first principal energy level. In the first principal energy level, there are 2 electrons. So therefore, 6 minus 2 is plus 4. Effective nuclear charge for carbon is plus 4. What about nitrogen? Effective nuclear charge for nitrogen. Nitrogen atomic number is 7. Effective nuclear charge is equal to nuclear charge minus shielding effect. So therefore, shielding effect is 2 plus 5. And then tell me which one has the highest radius. I told you that effective nuclear charge and atomic radius, the relationship is inverse. They are inversely proportional. So therefore, we can say that carbon has the highest radius than nitrogen. Okay. So the effective nuclear charge felt by the valence electron nitrogen is greater than effective nuclear charge felt by valence electron of carbon. Yeah, that is correct. Yeah, that statement is correct because effective nuclear charge value for nitrogen is plus 5. Effective nuclear charge value for carbon is plus 4. That's correct. Fourth statement, among the ions sodium plus, magnesium 2 plus, potassium plus, and calcium 2 plus, the two ions are ions closest to each other in size are potassium plus and magnesium 2 plus. Is that correct? They have given that potassium plus and magnesium 2 plus, the radius are very close to. Is that correct? You can see that in potassium plus number of electrons are 18, magnesium 2 plus is 10. So how we can say that these are very close atoms in radius? No, that is wrong. That is wrong. Electron gain energy of carbon is negative. Yes, most of the electron gain energies are negative, except nitrogen, beryllium, and magnesium. Their electron gain energy values are positive because of their stable configurations, right? But most of the elements are the negative electron gain energy values, right? So therefore, they are asking here the incorrect statement. So incorrect statement is number 4. Question number 18, answer is number 4. Right, okay. Question number 19. The increasing order of the second ionization energy of beryllium, boron, and oxygen. Beryllium, boron, and oxygen. So we know that according to the second ionization energy graph, that zigzag variation is like this. Right? So therefore, you can compare these three elements. Who has the highest second ionization energy? Here, beryllium, boron, oxygen. So the highest energy belongs to oxygen, then beryllium, and the least one is second one is boron, and the last one is beryllium. So therefore, so this is I2. So question number 19 answers. Question number 20. The shapes of F3ClO, FClO2, and FClO3 are respectively. So chlorine is the central atom, right? So it connected to three fluorine atoms. So therefore, we can draw the shape of molecule, right? We have to draw the correct shape of molecule. So we can draw that. 1, 2, 3, 4, 5. 3, 4, 5, 6, 7. Okay. Next one is FClO2. So therefore, then FClO3. So we can see that shape of molecule. So this is actually seesaw shape. This one, trigonal pyramidal. And this one, tetrahedral. Right? So question number 20 answers number 5.